To round out this course, we will examine a very special type of motion known as an oscillation. This video will look at two examples of oscillations and analyze the motion using ideas we have already developed. Here is a 2 kilogram object on a vertical spring. The spring has a spring constant of 40 newtons per meter. The object will expand the spring until it reaches equilibrium. At equilibrium, the object experiences two equal and opposite forces, weight and the upward pull of the spring. We can work out that to provide this pull, the spring has to get stretched to 0.4905 meters. We will set the origin at this equilibrium point. In an earlier video, we showed what would happen if you then further stretched the spring. For our example, we will stretch the spring by an additional 0.981 meters for a total stretch of 1.47 meters. We can calculate the potential energy due to gravity, as well as that due to the spring. Since the object is not moving at this point, the kinetic energy is obviously zero. So the total energy is the potential energy, which is 24.06 joules. But this time, we will analyze it in terms of forces and kinematics as well. At this point, when it is stretched by 1.47 meters, the upward force from the spring is greater than the weight. The total force, or net force, is upward. Using F equals ma, we can determine the acceleration. It is 19.62 meters per second squared. So at this point, we have information on the object's potential energy, kinetic energy, total force, position, velocity, and acceleration. Next, let's analyze what happens when the object reaches its equilibrium position. Here, we can calculate the spring potential energy and gravitational potential energy. And we can also work out what the kinetic energy must be. From this, we can work out what the velocity is. It works out to 4.387 meters per second, and it is upwards. At equilibrium, the spring force equals the weight force, so the total force is zero, which means, according to F equals ma, the acceleration is also zero. So once again, we have a wealth of information about this position. We can repeat this analysis for when the object reaches its peak. We can show that the object rises until the spring is compressed by 0.4905 meters. At this point, its energy is all potential. There is no kinetic energy, and once again, the velocity is zero. But now, something fascinating has happened. The spring force is now pointed downward. This makes sense because a compressed spring will try to push an object outwards, back towards equilibrium. The net force is easy to figure out, as is the acceleration, in this case, negative 19.62 meters per second squared. And we can deduce that since the net force is pointed downward, the object will accelerate downward. Eventually, the object reaches equilibrium again. The potential energies are the same as the last time the object was at equilibrium, so therefore the kinetic energy is the same as well. The only difference is, this time the object is falling through equilibrium, so the velocity is negative. At equilibrium, the net force is again zero, so the acceleration is also zero. Finally, the object reaches its starting point. The values of potential energy, kinetic energy, force, displacement, velocity, and acceleration are all exactly what they started out being. Once again, the acceleration is positive, so the object will start rising again. This motion will continue, repeating cyclically forever. We need to introduce some new terminology to describe this motion. First, the motion repeats regularly and exactly the same each time, so we say the motion is periodic. And the motion is always symmetric about the equilibrium point. As we saw, the object reaches a maximum displacement of 0.981 meters on either side. Periodic motion that is symmetric around an equilibrium point is called an oscillation. Now, the thing that causes these oscillations is really the spring force. At the object's lowest point, the spring force is pulling the object up towards equilibrium. Conversely, at the highest point, the spring force is pushing the object down towards equilibrium. The spring force keeps reversing its direction in response to the motion of the object, and it always points toward equilibrium. A force that always pushes an object toward equilibrium is called a restoring force. But at the same time, look at this pattern. The potential energy reaches its maximum value at the highest and lowest points, and at those points, kinetic energy equals 0. But at the equilibrium points, because of conservation of energy, kinetic energy is never 0, so velocity is never 0, which means the object keeps overshooting the equilibrium point. Oscillations occur because of two competing effects. One is the restoring force, always pushing an object toward equilibrium. The other is conservation of energy, always making the object overshoot equilibrium. While we have characterized the motion of the object at a few discrete points, we still need a general equation for it. We can do this by returning to F equals ma and expanding it out. The object is subject to two forces, the spring force and the weight force. The spring force varies between positive and negative values, but to keep things simple, we will write it as it is shown here. Now let's expand it. The spring force equals negative kx, and the weight force is mg. Now comes the trick. Acceleration is the second derivative of position, so we can rewrite the equation like this. Finally, we can move some terms around to yield the equation at the bottom of the screen. This is called a differential equation. A differential equation is an equation where a variable, like x, is expressed in terms of one of its own derivatives. This is a fairly sophisticated concept in calculus, but the equation itself is saying something quite simple. The position function equals the negative of its second derivative. There are only two functions that behave like that, the sine function and the cosine function. Since the object started at maximum stretch, the cosine function will be more useful for us. The position of the object over time is given by this equation. And when we graph the function, we get a shape that looks like the graph at left. As you're probably aware, a cosine function has two major parameters, its amplitude and its frequency. The amplitude is the distance from equilibrium to the peak height. That's just the original stretch, 0.981 meters. The frequency is the number of cycles, the number of up and down motions per second. By solving the differential equation, it's possible to work out that the frequency of the object is 0.712 Hertz. The object completes 0.712 of a cycle every second. It takes somewhat more than a second to complete a full cycle, in other words. When the motion of an oscillating object is given by a sine or cosine equation, we say the object exhibits simple harmonic motion. There are many examples of simple harmonic motion, and we will look at another one right now. Here is a pendulum. The bob has a mass of 2 kilograms. It is on a 10-meter string, and it is raised to a height of 0.15 meters before it is released. It is easy enough to figure out the initial potential energy, 2.943 joules. Its initial kinetic energy is 0. Now, let's look at the forces. We'll set the axes so that the y-axis is aligned with the tension. The weight force then needs to be broken into its components. the component in the y direction will balance out the tension, while the component in the x direction will pull the pendulum to the bottom of the arc. That's the equilibrium position. So the x component of weight is the restoring force in this case. Actually, I should be more careful. The bob is hinged at the top of the pendulum, so that x component of weight isn't really a force, it's a torque. The bob itself can be treated like a particle. We can solve its moment of inertia using mr squared. So we end up with a moment of inertia of 200 kilogram meters squared. And the torque is the cross product of the lever arm and force. We get 34.1 Newton meters. When the bob reaches its lowest position, both forces pass through the hinge point, so there's no torque. At the same time, the potential energy has entirely turned to kinetic energy, so the bob has velocity, and once again, it overshoots. Then the bob will swing to the other side, reverse course, end up where it started from, and the entire cycle will start all over again. We can apply Newton's second law for rotation to this system. Torque equals I alpha. Substituting for the torque, which we calculated earlier, and the moment of inertia, which we also calculated earlier, and using a definition of angular acceleration that related to angular displacement, we get this differential equation. It can be approximated as long as the angle that the bob was initially raised to is less than 10 degrees, as it was in this case. Once again, the solution is a cosine graph. Its amplitude is given by the amplitude to which the bob was initially raised, and its frequency is given by 1 over 2 pi square root of g over L, where L is the length of the string. This video analyzed two examples of oscillations, specifically simple harmonic motion. This is the basis of many applications, from ocean waves to musical instruments. For our purposes, this will also be the last lesson for this course. You now have everything you need to complete the project, and while we abridged a few topics, you have all the information you need to take Physics 104. As always, I'll be available by email or Zoom to answer any questions you have. Thank you, and above all, take care of yourselves.